My presentation today is a follow-up to the video titled, Will the LDF Model Work for Kinetic Separations? That is viewable on my YouTube channel. I discussed the reasons for the failure of the LDF model for kinetic separations that are either anti-synergistic or synergistic. The presentation is based on my paper in the new ACS journal, Chemical and Biological Engineering. That is, this paper is just available online on the ACS website. For modeling of mixture separation and fixed bed adsorbers, we need to solve a set of partial differential equations describing the variations of the molar concentrations of each of the guest molecules, C sub I, at any time t and position z along the fixed bed adsorber. And the differential equations are presented here. This is the component balance, where V is the interstitial gas velocity, Z is the distance coordinate along the fixed bed, epsilon is the bed voidage, Q super bar is the average loading at any position Z and time t in the fixed bed. The average component loadings are determined by solving the partial differential equations describing uptake of the guest components within the crystallites in the fixed bed. The surface of the crystallites is assumed to be in equilibrium with the gas mixture surrounding that crystallite, and the mixture adsorption equilibrium is described using the ideal adsorbed solution theory. N sub I represents the molar fluxes of ingress of the guest components within the crystals, and as I have argued in this paper and in several of my previous publications, the correct way to model diffusional influences for kinetic separations is to use the Maxwell-Stefan diffusional formulation that employs chemical potential gradients as driving forces for diffusion. Very few of the commercial software available in the public domain, such as Aspen and ProSim, employ the Maxwell-Stefan equations for determining the uptakes within the crystals. Most of the commercial software adopt the so-called LDF approximation, LDF standing for linear driving forces. Indeed, all the simulations I have published in the past are based on the Maxwell-Stefan equations, and dedicated codes needed to be developed, and the development has been in progress for the last 25 years or so. Rather than solve the partial differential equation describing transient uptake within the crystallites using the Maxwell-Stefan diffusion equations, most commercial software, such as those marketed by Aspen, ProSim, and others, adopt the so-called LDF approximation, where LDF stands for linear driving force. This approximation was suggested by Ergen Glukov in the classic 1955 paper cited here. Essentially, the time derivative of the component loading, average component loading, is assumed to be equal to the derivative of the equilibrated component loading, and this equilibrated component loading is in equilibrium with the bulk gas mixture at that position in the fixed bed adsorber. In the derivation of the Glukov approximation, it is assumed that the parameter d sub I divided by the square of the radius of the crystallite times the time t is greater than 0.1. Or the square root of this term here, which is the product of the diffusional time constant and the contact time t, is greater than 0.32. If we make this assumption, then as did Ergen Glukov, we can relate the time derivative of the averaged component loadings at any position z as given by this simplified expression that obviates the need to solve the partial differential equations describing the transient uptake within the particle. The limitations of the Glukov approximation are described in detail in my 2018 paper in Separation and Purification Technology. Watch also my video presentation on transient uptake of binary mixtures. So the question I ask here is this Glukov approximation good enough for kinetic separations? Let's first examine experimental data on transient uptake of carbon dioxide and ethane within DDR zeolite that consists of cages separated by narrow windows that are approximately 4 angstrom in size. The CO2 molecule, being a more slender molecule with a smaller cross section, has a diffusivity about 3 orders of magnitude larger than that for ethane, that has a significantly higher cross-sectional dimension. The experimental data for uptake of CO2 and C2H6 are shown here. CO2 shows a pronounced overshoot in its approach to equilibrium, whereas C2H6 approaches equilibrium monotonically. The LDF model of Glukov anticipates that both components would reach equilibrium monotonically, whereas the Maxwell-Stefan equations that use chemical potential gradients as driving forces correctly anticipates the overshoot in the uptake of CO2. The reasons for the overshoot is described in this paper and in several other papers I have published in the open literature. The overshoots are due to thermodynamic coupling effects that are the result of the use of the chemical potential gradients as driving forces. for diffusion. So the first conclusion is the LDF model cannot anticipate overshoots in component loadings. Let's see how the LDF model fares in describing the separation of mixtures of CO2 and C2H6 in a fixed bed adsorber packed with DDR zeolite. I consider separation of a equimolar mixture of CO2 and C2H6 entering a fixed bed adsorber at a temperature of 298 Kelvin. The partial pressures of CO2 and C2H6 are both 20 kilopascals, and I simulate the breakthroughs for the fixed bed adsorber, keeping the contact time between the gas mixture and the crystallites constant at the value of 3 seconds. L is the length of the fixed bed, packed bed, and V is the interstitial velocity of the gas mixture. So L divided by V is the contact time that I maintain constant. The radius of the crystallites are varied in such that the diffusional time constants, the Maxwell-Stefan diffusivity of component 1, which is CO2 divided by RC square, in this case is 0.5 per second. Here it is 5 times 10 minus 3 per second, 1.25 times 10 minus 3, and 2 times 10 minus 4 per second. In other words, A, B, C, D are obtained by increasing the crystallite size and reducing the diffusional time constant. In this case, of the diffusional time constant of 0.5 per second, the component that breaks through first is CO2. This is undesirable because what we would like is to selectively absorb CO2 so as to purify C2H6. The dashed lines are the simulations using the LDF model, and the continuous solid lines are the simulations using the Maxwell-Stefan diffusional formulation. If I take the diffusional time constant and multiply it by the contact time, I get a value of 1.5, and you will recall that the product of the diffusional time constant times the contact time should be greater than 0.1 for the LDF model to hold. So in this case, you will see that the LDF model works reasonably well, because the value of the diffusion time constant multiplied by the contact time is 1.5 seconds, well above the value of 0.1 that is mandated in the Glukov approximation. But this is not an interesting situation. We need to reverse the order of selectivities such that C2H6 breaks through earlier. For that purpose, we need to increase the radius of the crystallites or reduce the diffusional time constant. Let's take the value of 5 times 10 minus 3. If I multiply that with 3, I get a value of 15 times 10 minus 3, which is 0.0 0.15, and this value is significantly lower than the value mandated by the Grukov approximation of 0.1. And therefore, it is not surprising that the LDF model, even though it predicts the selectivity reversal, the quantitative agreement with the rigorous Maxwell-Stefan equations is rather poor. Indeed, if the diffusional constant is reduced further, the LDF model fails even more significantly in predicting the breakthroughs, and the agreement with the rigorous Maxwell-Stefan formulation is very poor indeed. Indeed, the productivity of purified C2H6 is significantly lower in the LDF approximation than anticipated by the Maxwell-Stefan diffusional formulation. From the breakthrough simulations shown on the previous slide, we can determine the productivity of purified ethane as a function of the diffusional time constant. The dashed line are the predictions of the LDF model, and the continuous solid lines are the predictions of the Maxwell-Stefan formulation, taking due account of thermodynamic coupling. We note that the LDF model underpredicts the productivity of purified C2H6 severely, indeed by a factor of about 2 to 3, lower than the value anticipated by the Maxwell-Stefan diffusional formulation. So the LDF model, it works rather poorly for anti-synergistic separations of mixtures of CO2 and C2H6 using DDR zeolite. The presence of nitrogen reduces the heating value of natural gas, and it is important to selectively remove nitrogen from natural gas resources, and this separation in remote locations is normally done using PSA technology, using barium ETS4, where ETS stands for Engelhardt titanosilicate. This material selectively captures nitrogen by tailoring the pore size such that only nitrogen is allowed to enter the pores, whereas the methane, being a slightly larger molecule with a larger cross-sectional dimension, is virtually excluded from the pores. I show here simulations of the breakthroughs for 2080 mixtures of nitrogen and methane using the Maxwell-Stefan diffusional formulation indicated by the solid black lines. The dashed blue lines are simulations using the LDF model. It is even visually obvious that the LDF model anticipates a lower productivity of purified methane as compared to the Maxwell-Stefan model implementation. The simulation details are provided in my paper that is online in chemical and biological engineering.